Okay, thin films problem number 5. This problem could be a little bit tricky, so I think you might need some help with it. I'll anticipate that. We got 31 bright and dark rings, called Newton rings, that are produced when this basically glass plano convex lens is resting on a flat glass surface, and the air gap in here basically counts as the thin film that's producing interference to produce bright and dark rings. How much thicker is it in the center than on the edge if there's 31 bright and dark rings? All right, I am going to redraw that, and let's see if we can sort this out a little bit. So I have the glass platform, and all right, the main thing I want to do is try and show the detail here. All right, so nothing happens where it touches. Basically, at this point you have a dark central spot, and that'll make sense when we consider that, you know, the light coming in, when the light comes in like this, there's a reflection, okay, and there's also transmission. Transmits through, bounces off down there, and goes back up here. Okay, and this path difference is the key thing. Now, the first thing that happens is, or the first thing to consider is at the glass-air interface. That's going from a denser medium to a less dense medium, or a faster medium. So, glass-air, there is no change in the phase. In other words, the reflected ray is non-inverted. So no, I'm going to say delta phi for a phase change. So this now means phase change, delta phi. At the air-glass interface, that's down here, well, it goes from air to glass. So that's a slower medium, and it inverts. So there is a lambda over 2 delta phi. In other words, there is a phase change. All right. So we have to consider that the light coming in then, you already have a half a wavelength of phase change because of the inversion that happens here. So the first place, so as we progress in this direction to bigger air gap, the first thing that's going to happen is we already have a half a wavelength phase change, which produces a dark region right at the center, okay, because half a wavelength is destructive interference. So the next thing we're going to see when we have a lambda over 2 additional path change, we're going to see a bright spot. So it goes bright, and then sometime later, say we're showing it here, it's going to be dark, and then later on it's going to be bright and then dark. Okay, I'm just illustrating the big picture here. Dark, bright, dark. So not including this, there's 31 orders. 31 orders. And that means 31 orders of bright and dark. So it's the dark that is really the controlling factor here, because it comes after the bright, not including the central spot. So bright, dark, 31 sequences of that. So what we're interested in is the conditions needed. Conditions for dark. Because once we set that up, we know we have to have 31 regions of that. It'll kind of fall into place. Assuming I haven't lost you already in this problem. All right. So for the dark, the path difference is equal to, well, we have cancellation. We need cancellation. So now we already have a half of a, we already have half of a wavelength here. We have a half of a wavelength because of the, inversion of this thing, of an inversion from the bounce from the air to the glass. So that produces a half a wavelength, which makes it dark. And then, so that's automatic. So subsequent ones, we need a path difference of lambda, which means m lambda for the different orders. So every additional lambda of path difference, we get another dark spot, which means that we have m lambda. Now I got to be careful. I'm going to say lambda n. The wavelength in the medium that we're talking about with an index of refraction n. In this case, the region we're talking about is air. All right. So that makes it easy, but that's the wavelength of light in air, not in the glass. So m lambda is equal to twice the thickness, there and back. Okay. So now that means we're looking for the thickness. We are looking for the thickness of this compared to this, corresponding to 31 orders. So we went through the trouble of figuring that out. So now the thickness is equal to m lambda sub n over 2. And lambda sub n is equal to lambda over n, and we've also got the 2 here. But n is equal to 1 because it's just the air. So this is equal to m lambda over 2. Lambda in air. Okay, so that is the condition. And so now that is basically the equation for the thickness. So m, worst case, is 31. The wavelength is 550 nanometers, so times 10 to the negative 9, and divided by 2. And 550, 10 to the negative 9 times 31 divided by 2 is equal to 8.5 times 10 to the minus 6 meters, which of course is 8.5 micrometers. And there we go. The hard part of this problem was sorting out what all this means, but the lesson to take away from this, as I've illustrated in the lectures on this as well, is to not just consider that the path difference is twice the thickness, because there and back, twice the thickness of the thin film, which in this case is air, but also to consider if there's any phase change at the bounces. No phase change, yes, a phase change. So you've already got half a wavelength from that. So we just, and that is producing destructive interference for the dark. So now we just keep adding another wavelength, which is why I came up with this formula. And that solves that problem. I hope that was not totally incomprehensible.